Okay, so in today's lesson, we are going to continue looking at how the resistance is affected by the dimensions of a wire. So in yesterday's lesson, we did an experiment in which we investigated how the resistance was affected by the length. We're going to review that experiment and then extend our work into other dimensions. Pardon the pun. So by the end of today's lesson, you should be able to state the relationship between the dimensions of a wire and its resistance, and also be able to conduct or carry out or answer questions that relate to the resistance and dimensions of a wire. So at the end of yesterday's lesson, I asked you to plot this graph. I'm hoping when you did that, you got a straight line that passes through the origin. Now, you should be comfortable now with telling me what that informs us about the relationship between these two quantities. If we get a straight line that passes through the origin, we can say that they are directly proportional to each other. And the way we can write that is saying that R is proportional to L. The resistance of a wire is proportional to its length. So let's have a look at how we can use this relationship, this proportional relationship, to answer some questions. So I've got a question here. Please make sure you get it in your notes. A student measures the resistance of a 1.2 meter length of wire to be 180 ohms. Calculate the resistance of another wire made of the same material and with the same diameter, but with a length of 30 centimeters. So we are going from 120 centimeters to 30. So we're going to be reducing the length of our wire. Now, how much of a reduction? Hopefully you can see that I'm actually dividing the length by 4. Now, with the proportionality, if I'm dividing the length by 4, I'm also going to be dividing the resistance by 4. So if we start out at 180 ohms, if I divide that by 4, I'm going to get to 45 ohms. So a really nice simple way of answering these questions. We just need to work out what I need to multiply or divide my length by in order to get from one to the other. In this case it was 4, and I just have to do exactly the same thing to my resistance. So what other factors are going to affect our resistance? We've already looked at a couple. Let's just recap those. The first one was the type of material that the wire is made out of. The second was the temperature of the wire, and we've just seen that the length of the wire is also going to have an impact. So what else do you think might affect the resistance of the wire? There's a bit of a clue in terms of some of the things I've been saying over the other lessons, and that is the cross-sectional area. I've talked about the fact that we need to keep the diameter the same. We're actually going to be looking at the cross-sectional area of the wire. Now, when I say cross-sectional area, I'm going to attempt to try and draw a wire here. Here's my wire there. I'm talking about that area here, the area, that face of that wire. So how does that cross-section area affect resistance? So we've got ourselves another practical. The title of that practical is Experiment to Investigate How the Cross-Sectional Area of a Wire Affects its Resistance. Like last time, we're going to start with our variables. So the independent variable this time is the cross-sectional area. The dependent variable is the resistance, and the control variables are going to be the material, the temperature, and the length of our wire. The diagram is far simpler than last time. I've got here a resistance meter. I'm actually going to use a multimeter in the video you're about to watch, set up as a resistance meter. And we're just going to connect that straight to a 5 centimeter long piece of wire, or several 5 centimeter long pieces of wire. It's really important that we keep that length the same. So what we're going to do, we're going to vary the cross-sectional area. We're going to use different wires, all of the same material, all of the same length. We're just going to change the cross-sectional area of each. Now, actually, we can't really directly measure the cross-sectional area. So what we're going to do is we're going to measure the diameter using a micrometer, and you're going to calculate the cross-sectional area of each one. And then we're going to measure the resistance. So let's go ahead and watch that video. In order to investigate the relationship between the cross-sectional area and the resistance of a wire, we need to measure the resistance of various different cross-sectional area pieces of wire. So what I have got here is 5 separate pieces of constantan. I've got 2 shown on the screen now. I'll show you the other 2 in a second. This first one has got a standard wire gauge. It's this SWG 36. Rather than looking that up on a table on the internet, what I've decided to do is get a micrometer out. This is a tool that you should be able to use. If you can't, I would suggest you go back and have a look through your notes that we did in September, because it is an important part of the course. So I've used that a micrometer screw gauge to measure the diameter of the wire in 3 separate locations. I've then calculated a mean. I've also run through here, I'll move that wire out of the way, exactly how we use that mean diameter to calculate the cross-sectional area. Something that I think is important here is the fact that I've converted that 0.25 millimeters into 0.00025 meters, so that the final area comes out in meters squared. So I've just halved the diameter to get the radius, squared it, and multiplied it by pi. I now need you to do the same thing for this SWG30 wire. So that has an average diameter of 0.37 millimeters. I've got 3 other pieces of wire on another piece of paper, so if you bear with me 1 second. So here I have another 3 pieces of wire. So this is SWG26, so that has a diameter of 0.32 millimeters. SWG24 has a cross-sectional area, has a diameter of 0.62 millimeters, and the SWG32 has a diameter of 0.34 millimeters. So you now need to calculate the cross-sectional area of the other 4 gauges that I'm going to be using. Get those into your table, and in a second we'll cut away to me measuring the resistance of those 5 different pieces of wire. So with this experiment, one of our important control variables is the length of the wire. So what I've done is I've tried to make sure that this is exactly 5 centimeters apart. So the length of our wire is 5 centimeters. We know from a previous lesson that the length of a wire is proportional to its resistance. So if I change the length of the wire, I'm going to change that resistance. So I need to make sure that that is kept constant with this experiment, because that's one of our important control variables. So this particular wire was our SWG 24, so that was the one with a diameter of 0.62 millimeters. So you should have calculated the cross-sectional area of that, and you can see here that that has a resistance of 0.8 ohms. So that's 0.8 ohms. I'm not going to show you me measuring all of these, because that's just going to waste time. So on the next slide, I'll show you a list of my results for each of the different wires that I just showed you. So you should have now watched that video. Now, I have only done one of them because it was just going to be boring, me doing it multiple times. But I want you to go ahead now and fill in your table and calculate all these cross-sectional areas. So here I've got them in ascending order of diameter. So you just pause the video and then please calculate those cross-sectional areas. So I'm hoping you've done those. If not, you're cheating. But here are the calculated values. Now what I've done here is I've put in the cross-sectional area bit at the top. So if you look at the header, I've got here times 10 to the minus 7. And it just means I don't have to keep writing that out over and over and over again. So for the 0.25 millimeter diameter, that is 0.49 times 10 to the minus 7 meters squared. And if we go through the rest of the list, we've then got all of those different calculated cross-sectional areas. And then the resistances I've measured are as follows. So the 0.25 millimeter, we started, with the 0.8. So that's the one I actually showed you, and the rest are there. So if you can copy those values into your table. Okay, I think I've given you enough time there. If not, just pause the video and get them copied out. Okay, so if we were to plot that graph, and I'm not going to ask you to do that. If you just do a sketch of it, you get this type of graph. And to be honest, it's not particularly very helpful. Unless it's a straight line graph in physics, we can't really do much with it. However, Some of you might recognize this graph as something that looks like it could be inversely proportional. We can certainly see that as the cross-sectional area increases, the resistance decreases. So just from that, we could possibly say that they might be inversely proportional, but just the shape of the graph indicates that it might be. Is R inversely proportional to A? Well, how do we go ahead and test this? There's two ways we can do it, and I'm going to go through both of them now. So method one for determining whether or not our data shows an inverse relationship is by plotting a slightly different graph. And I'm going to show you why we would do that. So we've got that R is proportional to 1 over A. So from your maths, you should be happy now with the fact that R is equal to K over A. So I've had to introduce this constant of proportionality, K. Now I'm going to write that out in a slightly different way. I'm going to write it out in the form of R is equal to K times 1 over A. Now those two things are the same. This statement here and this statement here are identical. They're just two ways of writing the same thing. Now the reason I've done that is because what I want to do is I want to compare it to the standard form of the line of an equation. So that is y is equal to mx plus c. Now, if you think about this, if I were to plot R on the y-axis and I were to plot 1 over A on the x-axis, our gradient would be equal to K, which is a constant. So if our statement that R is inversely proportional to A is true, if we plot resistance against 1 over the cross-sectional area, the one we just showed you was resistance against the cross-sectional area. This now is 1 over the cross-sectional area. Then we should get ourselves a straight line graph. And if you did that with the data that we've just gathered, cha-ching, yes, R is inversely proportional to A. Let's have a look at a second method of how we could do this. And I think even though I want you to recognize these graphs, I understand that if you do 1 over the cross-sectional area, you're going to get a straight line. I think this second method is probably more important for you to understand. So with the second method, we're actually going to start in the same place. We're going to start by assuming that R is proportional to 1 over A. And if we want to get rid of that proportionality sign and change it into an equal sign, we need to introduce this constant of proportionality, K. Now, what I can now do is I can multiply both sides of this equation by A, and we're going to get RA is equal to K. So what we're saying here is if I multiply the resistance in the cross-sectional area, I should always get the same value, this constant K. So here's the data that we collected earlier on, and what I'm going to do, I'm going to add an extra column onto my table, which is R times A. And I'm going to go ahead and I'm going to multiply all of these different values. So 0.49 times 4.9, 0.91 times 2.7, etc. And here are the values that I get. Now you can see they're not all exactly the same because this is a real experiment, this is real data that we've collected, so you wouldn't expect them to be identical. But I would say that they are all very, very close to 2.4. So they're within acceptable experimental tolerances. Now, I've been a bit naughty here and I've not included the unit. I probably should have done. For those of you that are interested, it would be times 10 to the minus 7 ohm meters squared. But it wasn't going to fit in the box, so I didn't put it in. Also, it's not really that relevant. All you need to know is that in order to show inverse proportionality, if I multiply the two values together, I should always get a constant. It should always be the same. And I would say that this data shows that that is definitely true. Cha-ching, yes, R is inversely proportional to A. Okay, so like with the length, I want to look at a couple of questions, because at the end of the day, most of the things that are going to come up in the exam are going to be questions like this. So let's start with this one. Make sure you get it in your notes. A student measures the resistance of a wire with a cross-sectional area of 0.06 millimeters squared to be 7.2 ohms. Calculate the resistance of another wire made of the same material and with the same length, but with a cross-sectional area of 0.3 millimeters squared. So we're going to do this in exactly the same way. I'm starting out with a cross-sectional area of 0.06 millimeters squared, and I want to get it to be 0.3 millimeters squared. Well, how do I get from one to the other? I multiply by 5. Now, With the length, because of the fact that I was making it 5 times longer, I would make the resistance 5 times higher because they were proportional. In this case, they're inversely proportional. So if I'm starting out with 7.2 ohms, rather than multiplying that by 5, I need to divide it by 5. And if I divide 7.2 ohms by 5, I'm going to come out with 1.44 ohms, which I'd probably then round to 1.4 ohms. So I had the same number of significant figures. Let's do another one, slightly more complicated. So with this one, I've got a student measures the resistance of a wire to be 24 ohms. Another wire is 3 times longer and has twice the cross-sectional area. Calculate its resistance. So I need to go from 24 to something, but I've actually got 2 changes that I need to consider here. I've got a change to the length and a change to the cross-sectional area. So let's have a look at those separately. Let's start with the length. I'm going to go from a length, I haven't been told what that is, but it's going to be 3 times longer. So what have I done? I've multiplied it by 3. So if I've multiplied the length by 3, what am I going to have to do to the resistance? I'm going to have to times that by 3, and I'm going to get 72 ohms. But that's what it would be if the only change I was making was the length. But that's not the only change. I'm also changing the cross-sectional area. Now what am I doing? I'm increasing that by twice. So I'm saying twice the cross-sectional area. So I'm multiplying that by 2. And if I multiply that by 2, remember this is inversely proportional. So I've got to divide my value by 2. So I'm taking my 24, I'm multiplying it by 3 due to the change in the length, and then I'm dividing it by 2 due to the change in the cross-sectional area, and I'm going to end up with a value of 36 ohms. So make sure you've got this in your notes. Okay, so we've got another question here. It's quite a complicated one, so don't freak out if you don't completely understand it, but have a look at it, see if you can process it. If not, like I say, do not freak out. So let's read it. It says a student measures the resistance of a wire to be 32 ohms. Another wire is 4 times longer and has a resistance of 16 ohms. If the cross-sectional area of the first wire is 0.5 millimeters squared, calculate the cross-sectional area of the second wire. So a lot going on in this question. We've got to try and break it down and look at it bit by bit. So we'll start by looking at the resistances of the wires. So we're starting out at 32 ohms and ending up with a second wire of 16 ohms. So what kind of a change is that? Clearly we're dividing by 2. So we know that somehow the changes to our wire need to end up halving our resistance. So let's have a look at the length. So we know that the length is going to be 4 times bigger. Now, if I increase the length of the wire by a factor of 4, the resistance is going to increase by a factor of 4. But we know that our resistance is actually half. So if I want to multiply it by 4, but end up it being halved, what do I have to do? I also have to divide it by 8. So the change to the length is making it 4 times bigger, but the change to the cross-sectional area must be making it 8 times smaller in order to achieve this reduction of a half. So what kind of change to the cross-sectional area is going to result in this resistance decreasing by a factor of 8? Well, if I start with A, remember, because it's inversely proportional, if I want the resistance to go down by a factor of 8, I need to increase the cross-sectional area by a factor of 8. Okay, so let's just go through this again, because I know this is quite complex. This increase in the length by a factor of 4 is increasing the resistance by a factor of 4. This increase in the diameter by a factor of 8 is decreasing the resistance by a factor of 8. And these two combined are going to result in the resistance being decreased by a factor of 2. Very complicated, but I'm hoping some of you will be able to follow that. So let's now have a look at where this ties back into our final answer. Well, I know from the question that our original wire has a cross-section of 0.5, and so if I want to increase that by a factor of 8, it's going to end up being it's going to end up being 4 ohms. 4 ohms. So that there is our final answer. Okay, I've got another one. Now, I just want to point out with these types of questions, they come up very, very infrequently. They are quite tough, so I wouldn't worry too much about them if you don't understand them. Don't start having a panic attack because of the fact that you can't do this type of question. But they have come up in the past, and if you can get it and you do understand it, that's brilliant. But if you don't, like I say, it's not the end of the world. This is more like an A-level question in terms of the level of thinking it requires. But let's go through it anyway. And if you do understand it, brilliant. If not, don't worry. So it says a student measures the resistance of a wire to be 540 ohms. Another wire is 1/3 of the length and has a diameter 3 times greater. Calculate its resistance. Now, some of you might have spotted that the reason this is more difficult is because I'm talking about the diameter here, not the cross-sectional area. And we'll have a look at what kind of impact that has. So like with the last one, I'm trying to go from 540 to something due to these two changes. And let's do them one at a time. So again, we'll start with the length. So the length is going from L to 1/3 L. So it's going into the third of its original length. So what have I done? I've divided it by 3. Now, if I'm going to divide the length by 3, what am I going to have to do to the resistance? I'm also going to divide that by 3, and I'm going to get 180 ohms. So that's what the resistance would be if that was the only change that I'm making to it. But it's not the only change. I'm also changing the diameter. So I'm making the diameter 3 times bigger. That's 3 times larger. However, this is where it becomes difficult. The relationship between the diameter and the area. Now that is A is equal to pi r squared. And this squared term is what makes it a little bit more difficult, because if my diameter, or my radius, is 3 times bigger, how much bigger is the area going to be? It's going to be 9 times bigger, because I'm squaring that factor. I'm squaring the fact that I'm making it 3 times bigger, and therefore it's going to be 9 times bigger. And if I make that 9 times bigger, what am I going to have to do to my resistance? I'm going to have to make it 9 times smaller. So I'm going to have to divide that by 9. And so the change in the length, making it 1/3 of the length, results in the length decreasing by a factor of 3. But by increasing the diameter by a factor of 3, I'm decreasing the resistance by a factor of 9. And that makes it come out to be at 20 ohms. Like I say, that is a really tough question. I can only think of in the last 15 years, maybe 1 or 2 questions in the IGCSE that's come up with, but they have been there. They could ask you one, but if you don't get it, it's not the end of the world. Do not panic. Right, I've created a Microsoft Forms question sheet for you. This has got a couple of very similar questions. The last 2 do require you to kind of have a go at this idea of the diameter changing. If you can't do them, don't worry too much. If you can, please do have a go at them. But if you can't, then don't freak out. Just do the first 5 or 6 questions. Make sure that's submitted by the deadline detailed on Show My Homework. Good luck, guys. So to finish off, I just want to summarize what we've looked at over the last 2 lessons. So you should now be able to state the relationship between the length of a wire and its resistance, i.e. that they are proportional. You should be able to state the relationship between the cross-sectional area of a wire and its resistance, i.e. they are inversely proportional. And you should be able to answer questions related to the resistance and dimensions of a wire.